Well, happy Tuesday again. So we've got trees up next that we're going to talk about. We'll spend a little bit of time building bad trees, again, for the fun of it, and kind of looking at what the structure is, how we can make them, and how we can make them faster and better, and those sorts of things. We're just going to talk about the project and then the next project. So let's do checkers first. Do a little checkers solver. Start up a new project here. Come on, there we go. This will be project 1. Just thinking about it. All right. So I like using a class for this because we track some information. We're going to keep the board around. We're going to keep our maximum numbers of jumps around. We could pass all of that to the function and just have a single recursive function do all of that work, but it feels like a lot of things to pass around. So I'm going to just make a class for checkers. And then we should probably take the board here. So we can take a different board. So any of this setup here for checkers, we should be able to go and do. So let me go make sure I'm following after here. Right. Oh yeah. So yeah. Okay. With and init. Yeah. And the max jumps for calculating one white checker, and then for all white checkers. So when we're ready to get our max jumps, then get max jumps here. We need to go find all the white checkers that we have, and then recurse. So for row in self board, and really we kind of need the indexes, right? The idea with that recursive function is we're probably going to have to pass the indexes here so we can track it around. So maybe we want the row index in the length, the range of the length of board, and then for column index in range, the length of self.board at the row index. Maybe. Again, you're probably going to have a square checkerboard, so that's kind of silly. But if we ever wanted to, now we could have a rectangular checkerboard if we're going off the length of our rows. Right? And then if our self.board at the row index at the column index is equal to a white piece here, or again, maybe we want to add some of these values up here. So maybe white checker equals a W. I don't know if this is all that helpful or not, but we can say, hey, if it's a self-white checker, then let's go do something here, right? So if we find a white checker, we're going to start that recursive function. So we can call probably a private get max jumps, and if we're tracking our max jumps, we probably also need a max jumps. Probably starts off at 0. We can come back to that as we go, and then we'll add our little helper function. So this will be a private get max jumps that takes a row index and a column index. So you can say, okay, so let's return, and not even return, sorry, because we want to keep going for each of these, right? So we'll just have to go figure that out. So we'll call self.getMaxJumps at the row index at the column index, because we know there was a white checker here. Right? So from here then, we need to start seeing if we can jump. So the logic is very similar every time. I'm not sure if the math actually makes it easier to turn that into its own function or not. So I'm just going to do them separately for now, and maybe we could make it cleaner, but I don't know. This one is just a little weird. So we need to see if from here I can jump, then we need to go try and jump, right? So that we're going to say, can we jump? If we can jump, right, then we will do the jump, and then we'll recurse, and then we'll undo the jump. Right, that sort of process. So first we can see if we can jump, and yeah, we can probably do this from each check here. So from this row and column, right now, one helper piece here is like is within range or isn't in board, or is a valid spot here. So maybe we'll have a define is valid location given a row index and a column index. Just because I'm going to do this a lot of times here. So if it's valid location, then it's going to say that the 0 is less than or equal to the row index, is less than the length of self.board, right? So check the row index, make sure it's a valid row index, and then, and my column index then is less than or equal to 0, less than or equal to 0. The column index is less than the length of self.board at the row index. Again, just in case we want to do rectangles, right? And then I want to check that the self.board at the row index, at the column index is equal to an open space. Right? I've got a blank here. Yeah.
And the 10th line, why do we, at the end of the 10th line, why do we say like row index again in the column and the brackets?
For this one?
Yeah.
So in case I wanted to make a rectangular sized checkerboard, this will make sure that the columns that I'm checking could be column 8, 9, 10, 11, 12, 13, 14, right? And maybe I still only have 8 rows. No one does that, but anytime we're doing a two-dimensional arrays, you usually want to make the columns off the length of your rows, just in case. So it's just a habit. It's not going to change any functionality for us. So this one then is a valid location, right? Am I going to land on a good spot? And it's blank, right? So can jump? So this is, if self dot is valid location. So I'm going to take my row index, and now if we're jumping, let's go maybe up left first. So it's -2 rows, -2 columns, right? So if that's a valid location, and then if there's a black checker at a spot. So this is like the halfway spot. So self.board at the row index -1, at the column index -1 is equal to a black checker. And again, maybe we'll call this a black checker. Do this black checker is a black piece. Just to be fun here. Okay, so if I can go there and there's a black checker in the middle, then we can go do that. Oh, that's not a private board, sorry. Right, that's our jumping up left, essentially. And then we can check, hey, can we jump up right? Can we jump down left? Can we jump down right? Whatever order we want to do those in, right? We have to then go do the jump, recurse, and undo the jump. So maybe we could even pass in here the values for blacks. We don't have to check this again. I'm feeling a little bad here. So trying to figure out where the black checker is based off of just a row index and column index doesn't really work, right? But we could give it, I don't know, black row index and black column index. So I could give it all those values then. So that one's blank then, and my self.board at the black row index at the black column index is equal to self.black checker. That one feels a little better. So I can check all of those at once then. Is it within bounds? And is there a black checker to jump over? That's getting a little long. Maybe I can bump that down. So the board is good, and that one's good, and that one's good, and that one's good. I gotta add all these silly slashes. Okay. So now I don't need this one, right? I can just say, hey, if I can go here, and then my black row index then is just -1, and column index -1. I guess this would be a little bit long for a function call, but and maybe not is valid location, right? Or can jump to maybe is maybe a better thing to call that. Oops. Come on, rename. Rename can jump to, right? So can I jump up left, right? If we can jump up left, then we're going to do it, right? And if we're going to jump up right, we're going to do it. If we can jump down right, on and on and on. So to do the jump then, right, we have a couple things. So we're going to take my self.board at the row index, at the column index, set it to blank. Take the white checker off because I'm jumping, right? And then put the white checker on where I'm landing, row index plus -2, and column index -2. Put the white checker where we're landing. Self.white checker, right? And then take the black checker off as well, right? So maybe we'll do that in order because it goes a little nicer. So self.board at the row index -1, at the column index -1 equals a blank as well, right? So move the white checker to here and take the black checker off. and then we're going to recurse. So this does the jump, right? So if I do the jump, then I probably count my self dot max jumps. I have number of jumps. Max jumps plus 1 is now 1. Now, tracking just max jumps here isn't really what we want to do here, right? Eventually we want max jumps, but I also need to know, like, on my current path, how many jumps I've made to see if that's longer than my furthest. So maybe we don't just update max right away, right? Maybe we have a self dot current jumps, starts off at 0, and then I'll increase my current jumps by 1. And then I can see if this is further than the max, I have a new max, right? So if self.current jumps is greater than self.max jumps, I can reset max. Self.current jumps. Now this is going to be a little tedious to have to do every time, right? So we can move it out into a function in a little bit here, because we count that as a jump. So that's doing the jump, right? And then we're going to recurse. So we're going to call self.getMaxJumps given this new location, right? So it's row index -2, column index -2. That's the recursive piece. Whenever this is done, we need to put the board back the way that it used to be. So we're going to undo all of these steps here, right? I like them in reverse order because it makes me happy. You don't have to, but I just like the symmetry. Right? So take away the jump. We're undoing the jump. Set that one back to blank here. Put the black piece back, black checker, and put the white checker back. Maybe we should do blank, blank. I don't know, is that silly? Self.blank, blank. That's too many similar letters here.
So,
yeah.
In the line where you, in 22nd line where you have -1, is this supposed to be a black checker?
Yeah. So we're taking the black checker off because we're jumping over it, so that removes the black checker from the board. Yeah. So we know there was a black checker here because our function checked to see, hey, there was a black checker here before we can jump to.
Then after we jump to a place with like an empty one.
And then we'll put it. Yeah, we make it empty, and then we start recursing. So the undo step then puts it back to a black checker. Yep. Now, all of this we're going to have to repeat every time. And if you have to repeat every time, that's kind of obnoxious, right? Wouldn't it be nice to have a function for it? Yeah, it would be. So like do jump, I don't know, or something. Do jump. Now I need to know where I'm starting, where I'm landing, and what's in the middle. I need a bunch of things, but that's okay. So the row index, current row index, current column index, the black row index, the black column index, and then the destination row index, and the destination column index. This gets a little silly here, but that's okay, right? It's our function. We can write it however we want. So we're going to do all of this. Probably make that a helper function too, right? So then the current row index, right? The current column index, the black row index, and the black column index, and then the destination row index, and the destination column index. Right? And then that can do the jump. Sure. We can even have it recurse. Yeah. We can do that. So this will be the destination row index, the destination column index. And then this is the destination row index, the destination column index. This is the black row index, the black column index. And this is the current row index and the current column index. Right? So if we can do that, then we'll call self.doJump. Now I have to give it all those things. So the row index, the column index, the row index -1, the row index, column index -1, the row index minus 2, excuse me, minus 2, and the column index minus 2. Now that's not so bad, right? And then I'm just going to repeat that now 4 times. Now, if I just have 4 different values, I'm doing the exact same thing. Yeah, we could turn that into a different function, right? Yeah, why not, right? We could. So probably need to set up all those values, right? What the destinations are and then the halves of them. So we could say, I don't know, jumps then could equal a tuple of tuples, tuple of tuples, right, with minus 2, minus 2, and then to go, that's up left, right, to go up right is minus 2 plus 2, and then to go so to go down right is plus 2 plus 2, and then to go down left is plus 2 rows minus 2 columns, right? So that could be the list of possible jumps. And then for each of those jumps then, we're going to do that, right, with our row index offset by here, and then the black ones are just half of that, right? We can divide those all by 2. So for jump in jumps, if self.canJump2, all right, canJump2 wants the row index and the column index, and then the black row index, oh, I'm sorry, no, that's the destination, right? CanJump2? Yeah, it's the destination. So it'll be the row index plus the jump first value, right? And then the column index is the column index plus the jump second value, right? And then the black checker then is half of that. So the row index, let me bump that down one maybe, divided by 2, divided by 2. Now, make sure we're forcing our order of operations. It should happen, right, because division touches, but just to be explicit here, right, never hurts. So if we can jump there, right, does that jump make sense? Some of these parentheses are a little funny here. If we can jump there, then we go do the jump. Is it silly to have to call it twice? Right, because we say if we can jump, then go do the jump. Right, maybe we try this try. Let's rename this one here. Try jump 2. So at the end of that, then instead of just returning, we can say, hey, if I can, then go do the jump. Self.doJump. Oh, but doJump needs to know where we're coming from. Shoot, do we have to pass more values? Now we have to pass more values. That's fine, we can do that. So we can have, let's rename all of these ones here. Let's just use these same ones. Well, I mean, really we don't even need a second function. We can just do all of it here. Let's do that. Let's rename this one here. I keep changing my mind here, I'm sorry. We'll just call it try jump. So we need that, and if we can, then we'll go do that. So this is the destination row index, right? Destination row index, and the destination column index, and the destination row index, and the destination row index, and the destination column index. So if that's true, if we can jump that direction, then go do the jump, right? Counter jump, do that sort of thing. And then for getting the max jumps, we're just going to try it. Self.try jump. Now try jump needs the current row, so that's our row index, column index, and then it needs the row index plus the jump, right? Because it's the, oh no, the black row index next. So it'll be the row index plus half, and then the column index plus half, and then it needs where we're going to land, so it'll be the row index plus the jump at 0, and then the column index plus the jump at 1. Let's set it up. Needs more slashes. 4. All right, hang on, let me just bring it all in one line for a second. See if we can make it happy, and then I can break it up. That, yeah, matches there. An illegal target for a variable annotation. Try jump. No, we need try to jump. Why is it unhappy? Oh, we had a colon at the end. Because it's no longer an if that's going to return a value or not. We're just going to try and jump that direction. It's a little messy with this, and this function is doing a lot, but I think that's okay. Right? So for every white checker we find, start get max jumps. Get max jumps then says, okay, let's try and jump from here, 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 here. Right? Eventually, we're going to recurse in here with get max jumps again. Right? At a new location, try to jump every location, all the different directions. Try it and try it and try it. We should be counting our jumps as we go. Right? Setting up max jumps, and then we're done with get max jumps. Right? For every white checker, we can return self.max jumps. I think that's about it. So we should try and build a board and try it out. So we can make a board equals, I want list of lists, right? So we were going to set up, here's a space. Let me do 8 spaces. So 1, 2, 3, 4, 5, 6, 7, 8. And I need 8 of those, right? 1, 2, 3, 4, 5, 6, 7, 8. All right, so we have 8 spaces. Let's try some. So if I have a white checker here and a black checker here, it'll land there. And then maybe we could go that way, or maybe we could go this way. And then it'll jump to there, and maybe over here we add another black checker, it'll jump to there, add another black checker over here, and one over here. So it should be able to go around in a circle, essentially, I think is the plan. And if I wanted to do one more black checker here, I could go over all 8 probably, right? There's a couple of different ways I can get 8. So I'm going to make sure it's going to try all the different directions here to get us 8 jumps, essentially. Should be good for us counting. So let's try it. So we'll say checkers is my checkers solver given the board. And then I'm going to print checkers.getMaxJumps. Should go back in 8. Again, we could write some unit tests, but that's probably okay for now. Uh-oh. Indexes must be integers or slices, not floats. Oh, when we divide by 2, we need the floored division by 2 to make sure it's a, where were we doing that? It's an integer value, right in here. So floor divided by 2. Here. That'll probably be a little happier. All right, we get 8. Look at that. All right, so if we take 1 out here, right? If we take this one out, our max should be 1, 2, 3, 4, 5, 6, I think. Probably 6, because we took that cycle out, but it'll have a couple different paths it can take. We're doing some poor testing here, but that's okay for now. All right, so that one seemed to work. What if we added another white checker? What if we had a white checker over here? We should be able to get 1, 2, 3, 4, 5 from this one here, right? And this one should be able to go 1, 2, 3, 4, 5, 5 as well. Should be 5. We have 2 checkers, right? We got 5. What if we had a white checker over here? So I can get 1, 2, 3, 4, 5 as well. 1, 2, 3, 4, 5, 6. And the other one gets 6, right? 1, 2, 3, 4, 5, 6. Should be better than 1, 2, 3, or 1, 2, 3, 4, 5. So it should be 6. We're just kind of trying some different boards and testing it out. We got 6. So I feel like it's doing pretty good here, right? So we can get the max number of jumps for one white checker. We get them all for all white checkers here with our checking for each white checker, right? If there's a white checker, start the recursive call. The recursive call tries it all and will recurse. So it's not directly calling itself, but the function it calls itself. So it's still recursion. So if you didn't have another function call itself, that's okay, right? It can do like a two-step call through here, right? And we didn't need to turn this into a function that takes 6 different values. I think that was better than having it copy pasted in the jump up, jump left, jump sort of thing. That would work just as fine, right? And then hopefully it's readable, right? We know where we are, what the black checkers are, what our destination is, where we're all going. So if we name things nicely, hopefully that works out well, right? That feel good? All right, awesome. So let me go commit that to GitHub here. This one. Here we go, project 1. So again, recursion is fun. It's a nice solution for some things. Now, we could have done this without recursion, but having to track all of these pieces would essentially mean we would need some way of keeping track of where we've been to undo it, putting them in some sort of list or modifying it all, because we're essentially tracking these 6 values every time now, right, for each one of the jumps. So it gets harder, but it's doable with iteration, with an iterative solution. I just wouldn't recommend it. Doesn't sound like it'd be a lot of fun. And with checkers, we're not going to have this crazy number of like calls that it gets so deep. I don't have thousands of jumps I'm doing, right? I know the board's a limited size, so that helps make it, I know this is a fine solution. We're not gonna run anything crazy. Like with Fibonacci, we had, we're adding up millions of ones. Super inefficient. We're only up not even 64, right? Because they're every other piece. So at most we'd have like 31 jumps. I don't even know if that's possible, but at most we would, right? It won't be too bad. All right. Cool. So let's start some new stuff then. Let's talk about trees. So this is week 7 trees. And then let's take a minute and look at our schedule again here. We've got break next week, right? Which it's sunny and kind of warm today, but it'll probably snow again next week, just in time for spring recess, which is still not spring. So we're going to talk about trees this week. We already had our lab. So when we come back after break, we'll do a lab on 3.5 for trees, and then we'll do our midterm review. The midterm on 3.7, I don't care to watch people take tests. I will show up and watch you if you'd like. Just let me know ahead of time that you want me to watch you take your test. If not, you can take it anytime you want. I'll turn it on 3.7. As long as you get it in by 3.12, you sit and take it. It'll have about an hour and a half time limit, because it's designed that you could take it in class. Take it whenever you want. Not everyone likes to take tests at 2 in the afternoon. Some crazy people are morning people. Take it in the morning when you're freshest. Go for it. I would take it at midnight, 1 in the morning, because that's when I'm my freshest. I get my best work done middle of the night because it's quiet and peaceful. I've had my coffee and it's got good vibes. Right? That's okay. That's my schedule. So anytime you want to hit the start button, go for it. But within an hour and a half, you'll have to hit submit. Right? So from 3.7 up to 3.12. Whatever you want to do, it's fine. You'll agree not to work with each other. Generally, people are pretty good at that if I ask them not to, right? It's not meant to be hard. I'll give you last year's midterm. It's half quiz questions and half 3 short answer programming, maybe long answer programming questions, like write a function that does this, or write something that does this.
Are these going to be recursive functions?
So we'll have one on recursion. We'll have one on stacks and queues. I got to remember what the other one is here. Probably one on object-oriented programming and tests, sort of thing. So when I time these things and plan them out, I imagine that those questions would take you maybe 10 minutes each, so that if you needed double the amount of time, that'd be 20 minutes each, gives you an hour for that. And then the rest of your half hour would be for the quiz style questions, which are pretty quick. That's just the goal. So if I expect you to do it in 10 minutes, it would probably take me, I should be able to write it in like 3 minutes or so for those questions. Again, I wrote them. I've done it before. So that's how I kind of time things. Like that's a 3-minute question for me, triple it for you guys, and then give you double. Like it's just estimating, because some things take longer than others. We'll do that on midterm review on 3.5. So we're going to talk about the next project today. I was going to have that due on the 12th as well. So hopefully you can take the break, and then so we can work on it this week, take a week off, work on it the midterm week if you want, and up to 3.12. So it's the usual 2 weeks without the recess week in there, right? So hopefully you can actually take a break. I think that should be fine, because we can do the next project we do then. Then we'll have a month for the final project. That should work out really nice. Yep. Okay. All right, so we're going to talk about trees. So trees are fun, bless you. They're a different way of storing data. So basically everything we've done so far has been data in a list, right? Sequential sort of data. Not everything follows that sort of pattern, right? So if you think back to your biology class, there's this hierarchy of classifications. We have kingdom, phylum, class, order, family, genus, species. I don't know why that's still in my head, but it's been in there for a really long time. Where everything that is a mammal, right? For the mammal, is that an order? I forget where that one falls in, but all mammals share a given type, right? We talked about this like with inheritance, right? So to represent sort of hierarchical data, we don't really have a way to do that, right? We only have ways to put things in lists. So you might have a list, and then it might have a list of lists, and it starts to get pretty messy here. So a tree allows you to store data with a parent and child sort of relationship, right? So if we write a class for tree, define its init, it might take some data here. We'll have self.data is the data, and then it can have self.children is a list, right? And then if you want to add a child, we'll say, okay, sure, let's take self.children. We need to take some data here. So, and we'll append the data. Right? Now, this sort of works here, but can your children have grandchildren at this point? In this hierarchy here, if I just append regular data, no, we can't do that. So what we're going to do is we're going to append a tree of that data. So all of my children will be trees, and all of their children will be trees. So we're trees all the way down. So this tree structure is recursive in nature. So it's a tree made up of trees, made up of trees, made up of trees. That's why we have to talk about recursion first. So it's this idea that it's made so that it's all trees all the way down. So if I wanted to know, say, how many items were in a given tree, I would need to know myself, I'm one, and then plus all of my children, plus all of their children, plus all of their children, plus all of their children, and I don't know how many generations there are necessarily, right? So if I want to have a count number of items or something, number of items, I'm going to return 1 plus, well, that's me plus the I want to add up the sum of all my children. Maybe can I do sum? I don't know if I can do sum. I think I need to say for child in self.children, let's add those all together. So let's take our sum is 1, sum plus equals child dot number of items. And we're done, we'll return the sum. Right? That's a function call. So for every child, right, call the number of items function, which will add 1, and then keep on, I probably shouldn't call it sum, so maybe total. Let's do total. Right? So we'll keep on counting, then we'll ask all of our children to count themselves, which is 1, plus count all of their children, plus count all of their children, plus count all of their children. So this call itself is recursive. Right? It's not recursing on the self tree, but it's recursive on the child trees, right? So it's not calling necessarily the exact same function of itself, but it's calling the same function on other selves, other children. But the function itself is being ran a bunch here. So if I want to make a tree then, so I'm going to say here's a tree, and we'll give it, let's just use some numbers, right? Because that's probably easy. So tree.add child, let's add 2. And then tree.add_child, we'll add a 3. And then tree, now children of 0, right, is going to be the 2 here. Right, so maybe we'll call that 2. Is the children at 0. It's probably a little improper I'm giving direct access, but this is just just to experiment here. We're not actually going to use this tree class. This was a throwaway here. So then I can say 2.add_child, and I can add 4 to that one, right? And then 4 would be 2.children of 0, and I could add a child of 4, and add a 5, and then we go back to the regular tree and add a child. If we have 6, right? And then 3 would be 3 is my tree of 1, or children, dot children of 1, right? That should be this one we added here. And I can take 3, dot add child of the 7. So eventually we should have 7, right? So we're going to have a couple generations. We'll have tree, right? If we kind of draw this out as a picture. So drawing this out is pretty helpful usually. So let's draw. So we had a 1 here, and then we had a 2, we had a 3, right? Then we said, okay, 2 is the first child. 2 add a 4. Okay, so 2, we add a 4. And then 4 is 2's first child, sure. 4, we add a 5. Okay, so 4 has a child of 5.
So like 3 had no children.
Nope, not yet. So 4 got 5, and then we add a 6 here. So we come back here and we add 6. And then we get 3, which is the second child, and we add a 7 to 3. Nope, that's a 7. Not a 3. I don't know why. I think I said 3. 7. So it should look something like this. So when you think of trees, right, you think of levels. So like this is level 0, level 1, level 2, level 3. Right? Each generation is the next level, essentially, when we count these. Trees also have a height, right? How high is a tree? How tall is it? How many levels is it in a given tree? Right? It's just the height of the tree. So the height is the maximum level. Right? So we'll look at how we can calculate that in a minute. So what I should be able to get then, if I print my tree dot number of items, we expect it to be 7. And we get 7 back out. So it added them all up. And I can run this in debug mode if I want here, which is super fun, right? So run this in debug. And I'll see then I have a self is me, right? I'm a tree, and I have children. Children at index 0, index 1, and index 2. So index 2 is the child of 6. Index 1 is the child of 3. Index 0 is child of 2, right? 2 has children. That child has children. That children has no children, right? Finally out of children here. Grandchildren or great-grandchildren or whatever this happened to be. You run out of greats at some point eventually. But we can kind of explore and see that relationship between them all, because they're all trees. Trees all the way down. Okay? So we can calculate the number of items in our tree recursively. We could calculate the height of our tree. Right? So the height of our tree then, we said was going to be the max level. Now, the tricky part is when you look at a tree, does one know how many levels it has? No, we'd have to like recurse going all the way down. Right? Another way you can count it is you can see how many parent generations there are. So for any given node, you can calculate the depth or its level. So usually you'd call that the depth. How many generations are there above it here? So for any tree, I can see how many parents it has. Right? My tree has the children, right? So I have to count the children. I don't have a way to reference my parent generation right now. So if I have a tree, it doesn't know who his parent is. I only know the children of a tree, so I can't calculate it that way unless I want to add a different way to track these things. Right? So you could have a self.parent equals the parent, and we could say my parent, we're going to default it to none unless you tell me otherwise. Right? So when I add a child, I'm going to add the data and self. I'll be the parent here. So now I have that parent relationship. So I can, let's do depth of a given tree. So for the depth of a tree, I'm just going to work my way up. So find the parent, find the parent, find the parent, find the parent, right? And that'll be my depth. So we'll start off at 0, and while my self.parent is not, well, I don't even want self, right? So I'm going to say maybe current is self, and while current.parent is not none, let's take current, set it to the current's parent, and we'll take my depth plus 1. I found a parent. Like we did with the linked list, we said, okay, go to the next one, go to the next one, go to the next one, go to the next one. We could walk those linked lists here using those nexts. So instead of next and previous, we just have the parent. Go to the parent one, go to the parent one. So if I have a parent, my depth goes up by 1. If that one has a parent, the depth goes up by 1. If that one has a parent, the depth goes up by 1. If that one has a up and up and up and up and up and up. So we can calculate the depth of any spot here, of any tree, based on how many parents there are in that tree. right? So the tree of 4, right here, right? The tree of 4 is going to have one parent and 2 parents, or its parent will have a parent, right? So we would say, hey, its depth is 2. It's at level 2, right? These are like depth or level. So a tree with no parents is at 0 depth, right? There are no parents above it. So if we ask for the depth of 1, the first tree, 0, right? All the way down, right? So we'd get 3. So to calculate then our height here, we could go through. So to calculate the height, define height of a given tree. We want the maximum depth. So I need to go ask all of my children for their maximum depth, and which will ask all of their children for the maximum depth, which will ask all of their children for the maximum depth, on and on and on. So I want to get the depth of all of my children. So I'll say my depth is 0 to start, I guess. And then for child in self.children, we want to find the max depth. So I think we can actually do that with max of self.children, or is it depth? Child.depth for child in self.children. I think you can do it in one line like that without a loop, right? We can say, okay, for every child in the children, find the maximum depth there. But that's only going to be the maximum depth for the children. That's not going to get the children's depth, right? So this would only find the maximum depth of my children, which is going to be 1. It's not going to recurse yet. So we need to make sure we are doing that recursive step here at some point. So one of these has to be a recursive call, right? So I want to find then all of the children and 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 all of the children. I want to find the furthest down child, right? And then eventually find the depth of that. So maybe I have a list of children. Will be all of my children. So self.children. And then for children, child in children, I can add all of their children. Right, so I want to take children, dot append, child.children. So that's not even going to work, right? It's going to get kind of messy here as we try and, because I want to get every single child here in the tree, and I want to find out what the depth is. So depth will work its way up, right? So all I need to do is to ask for the height of each one in each next generation, right? So height can be the recursive piece here, then will give me the max of that. So I want to take the max height, child.height for child in self.children. But eventually we have to return something, right? So otherwise this call here is not going to do me much good unless I'm returning something. So like my height could be 1, right? But max of 1 is not going to give me enough of that information. So I'd actually be adding these as we go, or finding the maximum as we go. Or height needs to see, is my depth higher than something? Right, so maybe I'm just going to calculate my depth. So I can say, what's my depth then? So then my depth will be self.depth. I can see what the max of my children's height is, which want to be the depth. Oh goodness, I think I'm mixing this up here. Hang on, let me go look. I got to cheat here. I'm getting myself confused. Child depth height. Oh yeah, the max of the depth for each position, each child. Okay, max of the depth is going to be 1 plus the depth of the parent, okay. For every p in positions. That should do it, right? Return max depth. Oh, this position, okay, so self positions we didn't write yet. So self positions will give you every item in there. Where is it here? Did they write it yet? I don't think they wrote it yet. There's a position class. Children. That's cheating. Oh, okay, yeah. 1 plus the max of the height. Okay. This is the one I want here. This is their better. His earlier version we don't need. That's fine. There we go. All right, so calculating our height then. So there it is. This will be the private height for a given item here, because we need to know which item we're working on. That should be fine. So we want to get, if we have no children, that's a 0 here, right? And then if we have children, let's go through and find their height, which will be 1 plus something, plus 1 something, plus 1 something, plus 1 something for each of their children in here, right? So 1 plus, 1 plus, 1 plus. So this should calculate all of it as we go down the path. So we're going to say if my length of self children is 0, return 0. What does it not like about that? Oh, I missed the parenthesis. There we go. Return 0. Otherwise, we're going to return 1 plus. Now, this one is the public height. Right? We kind of wanted the private helper one in here. So we can go through and calculate them all out. So we've got the height. Oh no, this one calls itself. That's fine. Return 1 plus the max of self.height. Or we want child, right? C.height. Child.height. For child in self.children. I've got too many parentheses in here. There we go. So for every child, have them calculate their height. We'll get the max of that. And that calculation, right, will drill all the way down every generation as we go. So when I get all my children, have them calculate their height. Their calculation of height will either be 0 if they have no children, or for every child they have, keep on recursing, keep on recursing. So if we look at that height from our node here, it's going to say, okay, well that's 1 plus, that was the max of the height of 2, the height of 3, and the height of 6. Let's do 6 first. So 6 is easy. So if we look at the height of 6, it's going to tell me it's 0. This has no children. The height of 3 is going to recurse. So 3 will be 1 plus the height of 7, which will be a 0. Right, so this path then is 1, 2, which is correct here. 2 then will be 1 plus the height of 4, which is okay. Well, that's 1 plus the height of 3. 3 was 0, because it has no children. So I get 1, 2, 3. So it's going to go down all of those children paths and call the child, call the child, call the child, give me the height. We're going to add 1 plus. That was the piece I was forgetting here. So we're going to count ourself as 1. Because we count when you get to no children, you count 0. So usually we'd say, hey, it's 0 is the first, and then 1, and then 2, and then 3. But we're essentially saying, okay, if I have any children, I'm 1 plus them. And if they have no children, they're a 0. So we're counting them early because I know I have a child, essentially. Right? So then the height of this tree, then, we should be able to print. We did the number of items, so this is number of items in tree. And then the height of the tree. Height of the tree. Tree.height. Right, so we think that should be 3 with 7 items. Looking good so far. So if we want to go add another generation, right? Do you want to add that to the 7, or do you want to add it to the the 5 node here maybe?
Yeah.
Add another one. So we got to go find that. So when we added this child, so then 5 will be 4.children. Nope, children. It'll be the first child. And then 5, we can add a child of, say, 8, maybe? So that should add an 8th item and another generation. Now we have height is 4, and we have 8 items, right? Now what's cool though, right, this is the main tree, we could print the height of tree 4, right? So the tree at 4 is my 4.height. Right? So 4 only has one child, so its height should be 1. So because this is a recursive structure, each of these are their own trees. So this tree has a height, this tree has a height, this tree has a height. Right? They all have their own heights when we look at them starting in that position. So it's kind of a weird way to think about it here. So we run that one. The height of tree 4, is 2. The tree at 4, the height's not 2, right? Shouldn't be 2. Let's see what happened here. So let's put a breakpoint in for 4 height. No, we don't want there. So now we'll continue. All right, so don't want it there either. Let's continue. All right, so I'm going to get the height of 4. So 4 has some children, right? Its children has the value 8. Right? And there's no children after that. So that's what we expect it to look like. So step into our code. So we're looking at height. So the length of children is not none. So we're going to get 1 plus something. Now we want the height of every child in here. So now we're at self where our tree was 5. Why is the data 5? Oh yeah, 5. It is 2. I'm so dumb here. I'm sorry. I forgot to draw it in the picture. I'm sorry. Yeah, so we added an 8 down here. Why? Can I just scroll? There we go. All right, 8. It is 2, right? Because we have child and child. I thought we only had 1. I was super confused. That's what I get for not updating my picture. So that calculates correctly for the node there, that tree there, because trees are recursive, right? We'll talk more about trees. There's all sorts of other fun things we can do with trees, looking at specific types of trees as we go. So look at the binary tree next. That's a fun one. It's a pretty common structure. We can talk about the next project.
Are these all data bases? Like data structure?
Yeah. So a tree is a way to store hierarchical data. Right? They let us do that.
What was the difference between depth and height?
So
Are they the same thing?
the depth is essentially how far down in the tree are you? How many parents do you have?
Yeah.
The height is how many generations are below you.
So the depth is like from where you are to the ones above.
Yeah.
That's the one where you are to the ones above.
Yeah, and height is from where you are to the bottom. Yeah. Yep. All right. So the next project, we're going to use, it's not a linked list. We're going to use this idea that classes can point to the next value here. So it's linked objects. So we're not going to use a linked list for it, but our class will know what the next value is, just like a linked list knows what the next item was. We're going to use that concept, so help us practice that. So we're going to write our own polynomial operations calculator here. So a polynomial is a term, one or more terms, right? Polynomial, some n number of terms, but you got at least one, right? You've got at least one term. So we're going to have exponents and coefficients. We're going to pretend exponents are integers because that'll make our life easy, right? We don't deal with the non-integer exponents. Mathland can have that. We're just going to forget it. But coefficients can be floats, right? Because we need to have decimal places at some point. So when you look at term node, right, an individual monomial, right? It's coefficient and its exponent. Things we can do with terms are the term knows what comes after it. So if the monomial has a next, it's part of a polynomial, right? But each individual term is just its own. Here's the exponent, here's the coefficient, right? So we should be able to compare one term to another term, right? Is it equal to another? So 3x to the fourth should equal another 3x to the fourth, right? Those are equal terms, right? And then polynomial then has the chain of monomials. So polynomial knows what the first term node is, So we're not going to work directly with term node. Users are going to use our polynomial class. So one of our implementation details is we know we have these term nodes. We have these linked objects of term nodes. So you can create a new polynomial given a coefficient and an exponent. You can add two polynomials together. You can multiply two polynomials together. Don't worry about subtraction or division. Just pretend they don't exist. You can differentiate your polynomial. You can integrate your polynomial. Pretend 0 is your constant. We can forget about C here. We can represent our polynomial as a string, which should give us a string in descending exponential order. And anything to the 0 power is going to be just the coefficient, right? Anything to the 0 is always 1, so you get just the coefficient. So don't give me 13x to the 0, just give me 13, right, in your string there. And then let's round to 2 decimal places for our coefficients. And then does one polynomial equal another polynomial? Or does one polynomial not equal another polynomial? Okay?
Do we need to use stacks for that?
No. So a term will point to the next term. So if it's a monomial, there is no none. There is no next, it's none. If there's a next, then I know it's a polynomial. There's another term here. But we can work, polynomials can be n number of terms. So the polynomial class has at least a first. There may or may not be a next one after that first, right? So a couple fun things about math, right? And this seems really silly to have to point out here, but this is pretty important here. So 3x plus 4x. What does that equal? 7x. Did this monomial change when I added it? Did this monomial change when I added it? So I get a new polynomial result back out here. Right? When you add, when you multiply, your originals don't change. You get a new result back out. Right? When you integrate and differentiate here, we're getting a new result back out. We're not going to change the originals here, because the original is a fixed, this is the polynomial that it is. If you want to differentiate it, I'll give you a new polynomial. So I need to build a new polynomial with the result. So I can make a polynomial 2x to the third, 3x to the fourth. I can add 2 and 3 together to get the first. I don't know why I numbered them this way, but sure. I'd have 3x to the fourth plus 2x to the third, right? Print it out, prints out like that. I can multiply 1 times 2 if I wanted, right? So 2 was 2x to the third, and then 1 was 2x to the fourth plus 2x to the third. So if I multiply those out, I'm changing what 3 was. This one's going away. I'm changing the value of 3. Now I'll have 6x to the 7th plus 4x to the 6th. Right? You get each term in the first times each term in the second. Add them all together. Right? We have to think way back hard to polynomial arithmetic. It's not too bad, I promise. If you wanted to differentiate, right, you're taking your exponent minus 1. I'm sorry, you multiply your exponent by your coefficient. That's your new coefficient. And then you take the exponent minus 1. Right, so 6x to the 7th is now 6 times 7 for the coefficient. Exponent goes down by 1. And if the exponent is 0, don't worry about it. Right, it's okay. Just don't do that. We know weird things happen with math, right? You got to remember all the way back to calculus, but that's okay. And then integrate, right? We do the opposite. So you're going to divide, right, and then add 1. Is that the right order? I think that's the right order. So poly 1 was 3x to the fourth. So we're going to divide 3 by 4, and then add 1 to the exponent there, right? Oh no, that's 3/5. So add 1 to the exponent and then divide. I can never remember the order here. I have calculators. But we got to do it here. So again, that idea, we're going to make new polynomials anytime we do our arithmetic here. So the add and multiply let me use the operator. So here's a polynomial, here's another polynomial. I can use the plus sign, use the multiplication sign. Super fun.
I'm sorry, only one variable, right? Single variable, yes.
No, so there'll be as many terms as they have in there. Or for like x, you mean, for the variable?
No.
Yeah, they're all x.
Wow.
Yeah, the x is just, it's implied.
What changes the power?
I'm sorry?
What changes to the power?
Yeah, our coefficient and our exponents will change when we do things.
So like, we kind of just need to work with a like term, right?
So after you do the arithmetic, right, then you have to combine similar exponents. Right, so depending on, I think that happens more often with multiplication, but if you add them together like we did, right? This is right to the 1, to the 1, to the 1.
So like essentially the first step for all of them is to combine like terms, and then we perform like the differentiation, integration, or sum.
So polynomials should already be combined. So you shouldn't get a polynomial that has terms that need to be combined already. Right? So only when you're adding them together or multiplying them should you have to do something with like terms. Differentiate and integrate should be fine because we already had like, we did not have like terms, right? The polynomial class makes sure it doesn't have two different x squareds. Does that make sense? So if you keep that first, it makes all the other things easier. You don't have to do any combining. So the only time we're going to combine is when we add and multiply.
But what is the point of having different polynomials? Because like, if you're adding them, we need at least two, right, to add.
Yeah.
But in terms of integration, we just give the integration method a polynomial so it integrates it.
Well, so a polynomial will have a method for integrate. So like poly3.differentiate or poly1.integrate will integrate that polynomial. So poly1 had this value, and then we want to integrate, we'll generate a new polynomial of this value here that I can save, I'll call poly5 or something. Right, so poly1 doesn't change when I integrate it. It gives me a new polynomial result that I can save if I want, or just print it out or whatever I want to do with it, right? But we're not changing the original. So this will still be 3x to the fourth plus 2x to the third, because that's polynomial 1. So polynomial 1 will always stay like this. Even if I call integrate, integrate doesn't change polynomial 1, it generates a new polynomial result, which I can save as poly5, poly10, my new polynomial, whatever I want to call it. But poly1 doesn't change just because I called the integrate function on it.
So the polynomial we're going to work will always be the same, kind of. What changes is the method we're calling it.
You'll make a new polynomial based on the results. So when you add two polynomials together, we'll get those two added. But the original poly2, poly3 don't change. But I'm going to get a new polynomial result with two terms. When I multiply here, I'll get a new polynomial out with two terms here. Right? If I multiply two two-term polynomials, right, each term multiplied by each other term. So my first term multiplied by their two terms, my second term multiplied by their two terms. So I could have 4 different terms, but I might need to combine like exponents. So I might end up with less than 4 terms when I'm done, right?
All right.
So we got some time to work on this till March 12th.
3 weeks, right?
Yeah, so take some time over break if you want. Then we don't have to worry about it. Go have some fun. We can come back and work on it. So we've got Thursday class to talk more about trees, and then we're off. So the week after that, when we come back, we'll do lab and midterm review. And then we'll do midterm on anytime Thursday to the next Tuesday. I don't plan on coming at 2 o'clock to watch anyone take a test because it's terribly dull. Right? You're welcome to if you want. Just anytime you want to take it. And we'll talk more about that in 2 weeks from today, right? After we come back from spring break.
Yeah, well, the midterm is not due until the actual spring break, right?
Yeah, so after we come back from spring break, we'll have Tuesday for review day.
Okay.
And then that Thursday, I'll open the midterm on 3/7, but it won't be due till 3/12.
So I'll have approximately 5 days completed.
Yeah. Any point in that 5 days, you click start, and you have 90 minutes.
Okay.
Yep. Cool. All right, that's all we got today. We'll come back and do more trees on Thursday.